Hello everyone, this is Dr. Lennon, and we're going to look at the arc length formula today. So another application of integration, really just a pretty simple formula and not too much else to the section. So if you have a continuous function on some closed interval, then the length of that curve can be found by integrating from a to b of 1 plus the derivative squared, the square root of that entire quantity. So why don't we just look at a few examples and kind of leave it at that. Again, you can try and read the proof of this if you find it interesting, but mostly in our class we're going to focus on applications and doing the problems. A lot of times you wouldn't come up with the proof. It's not one that would help you remember the formula too much, but the formula is not too difficult to remember. Okay, so let's look at our first example. What we want to do here is find the length of f of x equals, let's say x to the 3 over 2 power, x to the 3 halves, from x equals 0 to x equals 4. Okay, so first thing to apply this is we have our interval, so we want to find the derivative and then plug that into what we're integrating. So let's just recall that f prime of x here is going to be 3 over 2 times x to the 1/2. So our arc length is just going to be the integral from 0 to 4 of the square root of 1 plus this quantity, the derivative squared. So 1 plus this 3 over 2 x to the 1/2 quantity squared dx. Okay, so that's the formula to find the arc length. So let's go ahead and simplify under the square root there. So this is the integral from 0 to 4 of the square root of 1 plus 9 over 4 x dx. So that's just going to be a straightforward substitution. We'll just let u be the entire quantity beneath the radical. So we got to use sub to finish this up. Again, let's let u equal 1 plus 9 over 4 x. So then du will equal 9 over 4 dx. Don't forget to translate your limits. Again, your x equals 0 limit will go to u equals 1. And your x equals 4 limit will go to u equals 9 plus 1, essentially, which is 10. So then our integral down here continuing is the integral from 1 to 10 of the, so don't forget the 4/9 in front. So I'll just write it as 4/9 square root of u du. And now we can find the antiderivative of that. So again, you're going to be adding 1 to the power of 1/2, which is 3 over 2, and then we're going to multiply by 2/3. So we're going to get 8 over 27 times u to the 3 over 2 from 1 to 10. And then you can go ahead and plug in the numbers. So basically we're getting 8 over 27 times the quantity 10 to the 3 halves minus 1 to the 3 halves, which is just 1. So 10 to the 3 halves doesn't come out, as an integer or anything like that. So we might just approximate that the length here is about 9.1. So I'm just going to write generic units because the problem doesn't specify meters or centimeters or anything like that. So that's the arc length formula. Again, a lot of these inherently are going to be a little bit messier. You're going to have some substitutions and things like that because we're taking the integral of the square root of 1 plus the derivative of our function squared. So that can make things a little bit messier. Okay, so let's go ahead and why don't we why don't we do an example where we look at something that we can compute the arc length from in geometry and show that it comes out the same. So what I want to do is, why don't we do, say, half a circle. We know the circumference formula for a circle. So example, and the unit circle is one we know. So let's verify with the arc length formula. That half the circumference of the unit circle is exactly pi. Right, and let's just recall that. So the unit circle in general looks like x squared plus y squared equals 1. So that's the circle with radius 1. We recall from geometry that the circumference of any circle would be 2 times pi times radius. The unit circle has radius 1, so half the circumference would have a length of just pi, half of 2 pi. What we have to do here is we have to solve for y. So basically, if you solve for y, you're just subtracting x squared, and then you have to take plus and minus the square root. And essentially, the top half of the circle has equation y equals the positive square root of 1 minus x squared. And then the bottom half has y equals minus the square root of 1 minus x squared. So we can pick either half. So this is the, let's say, the top half. And here we have the bottom half. So we're just going to choose the top half here. Again, we have our formula there. So what we need to first do is figure out what y prime is going to be. So we will use the formula from the top half. And plug it into the arc length formula. Again, the limits are going to be pretty straightforward because it has a radius of 1, so you're just going from x equals negative 1 to x equals 1. Again, you can use symmetry there too to simplify things even further. So we could just use the first positive quarter of the circle and go from 0 to 1 and double it if we want. So maybe we'll use that later. But anyway, so let's figure out what y prime is. Y prime is going to be, well, we're going to have a 1/2. Then we're going to have a minus 2x from the chain rule. And then that's going to be 1 minus x squared to the negative 1/2. So basically our y prime looks like, well, the 2's cancel. So we just have minus x over the square root of 1 minus x squared. So that's what we want to plug into our arc length formula. So our arc length formula is going to look like the integral from negative 1 to 1 of the square root of 1 plus this derivative quantity squared, negative x over the square root of 1 minus x squared quantity squared dx. And so continuing on, I'm simplifying inside that integral there. We have the integral from negative 1 to 1 of the square root of 1 plus x squared over 1 minus x squared dx. And now it'll probably be helpful to get a common denominator. We can write 1 as 1 minus x squared over 1 minus x squared. So we have the integral from negative 1 to 1 of the square root of this 1 minus x squared plus x squared over 1 minus x squared dx. So our integral is, in fact, just the integral of the square root of square root of 1 over 1 minus x squared dx. And again, that can be simplified a bit further as well. Negative 1 to 1, we can do the square root of the top over the square root of the bottom, so we can write it as 1 over the square root of 1 minus x squared. And then if you recall, this is just one of the trigonometric substitutions that we did in another video. So we just have to remember which trig sub that's going to be. You may want to pause the video and try and think about it, or go back to those notes and look it up, but we'll go ahead and do it. In fact, we don't even need a trig sub here. This is just the arc sine of x. In fact, the antiderivative. If we had other coefficients messing around, we could go back to one of those trig subs, but in fact, we don't need it here. So this is just the arc sine of x from negative 1 to 1. So we end up with pi over 2 minus negative pi over 2, which gives us exactly pi, which is what we wanted. Okay, so let's go ahead and look at some other examples. Let me just fish one out of the textbook here. Okay, so this one's similar to one I posted on the homework. This is x cubed over 3 plus 1 over 4x on the interval 1 to 4. Again, all these problems pretty much work the same. We're just looking to identify the derivative and then plug it into that formula. So we need to start here by finding y prime, which is just going to be x squared, and then 1 over 4x, remember that's like x to the negative 1, so it's going to be minus 1 over 4x squared now. Subtract 1 from the exponent, you get negative 2 there. So that's our derivative. So our arc length is found by integrating from 1 to 4 and plugging that into the square root of 1 plus this derivative that we just found, quantity squared. Okay, so probably the easiest thing here is to just multiply everything out. So again, remember that's going to involve foiling since we are squaring a binomial. So inside here we've got the square root of 1 plus x to the 4th, and then multiplying outside with inside and doubling it, you're going to get, I'll just write it all down. I'll say minus 2 times your x squared times your 1 over 4 times x squared. And then you're going to have plus 1 over 16x to the 4th. So that's everything that's inside the integral. Now we just want to simplify it. Sorry, that 4 looks a little messy. So 1 over 16 times x to the 4th. Okay, so this is going to be the integral from 1 to 4 of the square root. Okay, so the middle term there, it's going to be minus 2. The x squareds are going to cancel, so 2 over 4 is going to be minus 1/2. So we're actually just going to have a 1/2 here. And then we're going to be left with a plus x to the 4th and a plus 1 over 16 x to the 4th. And then in this one, actually, it almost looks like magically what we have on the inside of that square root is going to factor into a perfect square. So I just noticed that if you do, if you look at the 1/16 x to the 4th, that's 1/4 x, 1 over 4x squared, quantity squared. And the x squared term will also be there. So that's x squared squared. And then if you do 2 times x squared times 1 over 4x squared, you get exactly 1/2. So in fact, what's inside the square root there factors into x squared plus 1 over 4x squared, quantity squared. And you can go ahead and check that by foiling it out if you want, but it does work. So then that makes the integral much, much easier. We just end up with the integral from 1 to 4 of x squared plus 1 over 4x squared dx. And those are relatively simple antiderivatives. X squared is just the power rule, so it becomes x cubed over 3. And then the second one, you can rewrite it as 1/4 times x to the negative second. So if you add 1 to the power, it's just going to become x to the negative 1. So it's going to become a minus 1 over 4, and then the x in the denominator. And this is from 1 to 4. So we can go ahead and finish that off by just plugging those numbers in and subtracting. So we end up with 4 cubed over 3 minus 1 over 4 times 4, which is 16, and then minus 1/3 minus 1/4. So let's see, 4 cubed is 64, so we have 64 over 3 minus 1/16, and then we're going to have 1/3 minus 1/4 is 1/12, and then we've got the negative, so we've got minus 1/12, and then just some simplification to figure out what that fraction is. It looks like 48 is going to be the common denominator, so let me just figure that out and then we'll write it down. So this comes out to 1017 over 48, or about 22.2 if you round to 1 decimal place. That's pretty much it for arc length integrals. I'll say one more thing just because, so here's a remark. So many even simple functions will have arc length integrals that cannot be done by hand. So often we appeal to numeric methods. Numerical methods. So just using a calculator, or Desmos is another site I like very much. Let's just look at a simple example. Actually, as of right now, we wouldn't be able to do this one. So, e.g., if we looked at the arc length of y equals x squared from, say, 0 to 2. So, I mean, here y prime would be 2x, so your arc length integral would look like length equals the integral from 0 to 2 of the square root of 1 plus 4x quantity squared. So we end up with something that we're not able to compute unless we want to appeal to something more difficult. So I think maybe one of our trig things will do that, but it's not necessarily a simple integral. So this one I think will actually require a trig sub. So theoretically we can do it, but if we wanted to do it numerically, how would we do it? So we can just go to the website desmos.com, so desmos.com, and we can just type in the integral. So we can just do the integral from 0 to 2, and that one was the square root of 1 plus 4x quantity squared dx, and we get the integral there. So we see that it's approximately about 4.65, and that would do it for us. So that's a quick way to do a numerical one if you're getting stuck because the technique becomes too difficult or you don't see a technique that applies to the integral that we're trying to solve. Anyhow, that's it. This is Dr. Lennon signing off.